be going over question 2 from the week 7 worksheet. This question asks you to consider the Haber process, a process by which ammonia is synthetically created from nitrogen in the air. This question asks you to use your knowledge of equilibrium and Le Chatelier's principle to determine several important steps in the Haber process. The first one you're asked about is pressurizing the nitrogen and hydrogen gases to 200 atmospheres. So does this help create ammonia? If we were to look at the chemical reaction that's occurring, the equilibrium here, between a mole of nitrogen and 3 moles of hydrogen going to 2 moles of ammonia, if you increase the pressure, Le Chatelier's principle says that the side with a lower volume of moles is going to be favored. So in this case, that's the ammonia side. So increasing the pressure of the gases is going to push the reaction towards the product side, generate more ammonia. So that's a good thing. Why isn't this just so pressurized that we don't need to do anything else? And that's the cost of the pipes in the reactor. About 200 atmospheres is a reasonable pressure to drive this reaction towards the products but not spend so much money on the capital costs associated with the thick-walled reactors and pipes necessary for those temperatures. Part 2 of this question asks about heating the reactor. So the reactor, if we were to look at the process, is heated to about 450 C. Now, this reaction has a negative delta H. This means that heat is produced as a result of this reaction. So if we were to imagine putting plus heat on the product side and apply Le Chatelier's principle, you'd see that adding heat to the reaction mixture is going to drive it back towards the reactant side. You would think this is a bad thing for us to do. You would want to conduct this reaction at very cool temperatures to get as much ammonia as possible. However, in this case, you also need to consider the rate as well as the equilibrium. If you were to cool the reaction down, the rate would be very slow indeed, and it would take years to reach an equilibrium. Whereas at the temperature of about 450 C, that equilibrium will be reached quickly. Even if it's not a full equilibrium, if you get about 15%, you can always extract that product and recycle your reaction flow, or your reactor effluent, I should say. And we'll talk about that in just a second. First, the third part of this question asks you to consider adding argon gas to pressurize this reaction vessel further. Now that would not increase the partial pressure of any of the reactants, so it would not change the equilibrium. This, in the question, asks you to find a fictitious step. This is the fictitious step. There's no reason to pressurize the reactor vessel with inert gas. The next part of the question asks about the iron catalyst. What is the purpose of the iron catalyst? Well, the catalyst increases the rate and changes the reaction pathway, but it does not change the equilibrium. So we get just the same amount of ammonia out, but if you were to look at this energy diagram, here we start with our nitrogen and our hydrogen, and out here we have ammonia. You can see that in order to get it to react without the catalyst, we need to go over this huge activation energy. And that's very hard to do. Instead, we use this catalytic pathway, which allows us to reach this equilibrium much, much faster and make this a reasonable reaction to do in industry and gain a profit from. Finally, you're asked why this reactor effluent is recycled and liquid ammonia is removed. Of course, the most obvious answer is you need to get your product out, you need to remove ammonia. But considering the Le Chatelier's principle and the equilibrium behind it, as you remove ammonia, you're removing this product, which is going to drive the equilibrium back towards that product to make more. So if you only get 15% ammonia on your first pass through the reactor, you pull that ammonia out and you send the remaining nitrogen and hydrogen back into the reactor, and you're going to get it to continue making more ammonia. And if you keep that loop going, you're going to get a very high yield for that ammonia.